What's up, guys? It's Mr. Bringle, and today we're going to be going over the acceleration math problem examples. So there are 5 problem examples that we will work through together, and then you guys will work through the problem exercises on your own. So let's go ahead and if you haven't already watched the video over the different equations that we use for acceleration and the variables, please watch that. It's a quick video, about 5 minutes long, and then come back and check this video out. So this says that Grace is driving her sports car at 30 meters per second. So I'm going to underline this. When a ball rolls out into the street in front of her, Grace slams on the brakes and comes to a stop. That's going to be key here in 3 seconds. What was the acceleration of Grace's car? So in this problem, it's given us a number of things, and we have to be able to kind of pick out what we're doing here. I always have you guys write your variables, the givens and the unknown down. So one thing that we know is that's obvious here would be the time, right? So the time here is 3 seconds, and then it's given us a velocity, but we kind of actually have 2 velocities that it's given us, and you're going to be wanting to think about initial and final velocities in these types of problems. So she's driving her sports car at 30 meters per second. That is implying that her initial velocity is 30 meters per second. So I'm going to write that down here. VI is equal to 30 meters per second. Okay. And then it says that she comes to a stop in 3 seconds, which implies that her final velocity is 0 meters per second. And then it's asking us to solve for the acceleration of the car. Okay. So always think about in these problems, did the person start from rest? If so, the initial velocity would be 0. Or did the person or the object stop? And then the final velocity would be 0. So that's kind of how you'll want to attack those. Now, when we look through our equations, remember the process here is the first question you're going to ask yourself is, does this problem involve a change in position, delta x? And of course, obviously, Grace changes her position. But when I say that, what I mean is, did it give us change in position as a given? And the answer to that is no. Or do we need to solve for the change in position? And again, the answer is no to that because we're solving for acceleration. So immediately we know which equation to use. So if you have the equations up next to you, or you have that other video pulled up, we're going to use the first equation that we talked about, which is this one right here. The final velocity of an object is equal to the initial velocity plus the acceleration times the time. Okay, so now we can go ahead and plug these things in. 0 is equal to 30 meters per second plus, in parentheses, acceleration times 3 seconds. Okay, so the first thing that we need to do here is we need to get rid of that 30 meters per second. So we're going to subtract that off because these are being added together right here, right? So we have this addition sign. So if I subtract 30 from each side, that will get that off of there. Now I will be left with negative 30 meters per second is equal to 3 seconds times acceleration, right? So the next step here would be to divide by 3 seconds on each side. And that is going to give us an acceleration of negative 10 meters per second squared. Okay, so why is this answer negative? Well, in this case, Grace is slowing down, right? So in all of these acceleration math problems, you're going to assume, and they'll be treated like this, that the object is moving in the positive direction when it's on the ground, moving in a straight line. It's moving in the positive direction. And we know that because it identifies a positive velocity to start with. So Grace is driving her sports car at positive 30 meters per second. Therefore, if she slows down, her acceleration must be in the opposite direction of movement. So just remember, in class, we've talked about that. It's a common misconception that negative acceleration means slowing down always. That's not always true, because you could have an object that's slowing down while moving in the negative direction, which would be a positive acceleration. However, in these problems, all of them are going to have an initial positive velocity. So I just don't want you to get confused with that. Just make sure that you're still thinking about it as the acceleration is always in the opposite direction of movement when the object is slowing down. Okay, so let's move on here. It says King Kong carries Fay Ray up the 321 meter tall Empire State Building. At the top of the skyscraper, her shoe falls from her foot. How fast will the shoe be moving when it hits the ground? Okay, this has not given us a whole lot of information. The one thing that we know here is we do have a change in position, right? The foot is going to fall from 321 meters. So instead of using delta x, since this is a vertical fall, I'm actually going to use delta y. And delta y is 321 meters. Okay. And then we do know that we're going to be solving for the final velocity. So this when you're solving for final velocity when an object is falling, the final velocity is never zero. What it's asking for is the final velocity of the object just before it hits the ground, or what velocity does it hit the ground with. So it's not zero. You're going to be solving for that maximum speed that it reaches. So we know that we're solving for the final velocity, and I can't get this to write. Okay, but that's all we have. So what are we missing here? Well, there's a couple things that we actually have to imply. The first thing that we have to imply is the initial velocity of the shoe. And it's going to be the same as the initial velocity for any object that's dropped. What speed does it have initially? Well, it's zero, right? It was dropped from rest. So the initial velocity of the shoe is 0 meters per second. Okay. Now, it doesn't give us a time. We can't imply anything about that. However, because this is a free fall problem, we know the natural acceleration of that shoe. That is the acceleration due to gravity, or the acceleration that's caused by gravity, which is 10 meters per second squared. Okay. 10 meters per second squared. So at this point, now we can go ahead and we can choose an equation. Okay. So the first question that we want to ask ourselves is, does the problem involve a change in position? Meaning, did it either give it to us or are we solving for it? The answer in this particular problem is yes. We have been given the change in position. So that eliminates the first equation, the one that we used in the previous problem. And now we need to choose between the other two. Again, I numbered the equations in my previous video. The second equation is the change in position is equal to initial velocity times time plus 1/2 at squared. The second one is final velocity squared is equal to initial velocity squared plus 2 times acceleration times the change in position. So the question that we ask ourselves to differentiate between those two is, does this problem involve time? So it didn't give it to us, and we're not solving for it. Therefore, we cannot use the second equation, the 1/2 at squared. Instead, we are going to use this equation. Final velocity squared is equal to initial velocity squared plus 2 times, in this case, g for the acceleration, and also delta y. Okay, so I'm not going to penalize you if you put delta x there instead of delta y, but I do want you to be thinking about vertical and horizontal. So I would like you to put delta y. Okay, so let's go ahead and plug this in here. We're obviously solving for the final velocity that is squared. Don't forget that. That's equal to initial velocity squared, which is 0, right? Ignore that weird symbol there. Plus, and then we're going to have 2 times 10 meters per second squared times 321 meters. Okay, so we're going to end up with final velocity squared is equal to, you're going to do 321 times 10, which would be 3,210, and then times 2, so 6,420. Okay, and now what we need to do is we need to square root both sides because we want to get rid of that squared right there, right? So when we do that, you square root that number, you're going to get 80.12. So the final velocity of the shoe just before it hits the ground is 80.12 0.12 meters per second. Okay. All right. So we'll go ahead and move on to the next page here. And we'll look at a couple more examples. Okay, so on this one, it says the Steamboat Geyser in Yellowstone National Park, Wyoming. By the way, if you have a chance to go, it is unbelievable at Yellowstone. Is capable of shooting its hot water up from the ground with a speed of 48 meters per second. How high can the geyser shoot? So I like to draw an example here. So we've got a geyser and it's shooting water up like this, right? The water's getting shot up. Well, it says that it's shot up with a speed of 48 meters per second. Okay, so that is defining the direction up as the positive direction because it gave us a positive velocity. All right, so that means when it comes time to look at our acceleration here, remember that gravity is always pointed down, and therefore when an object is being thrown up in the air or dropping, g, the acceleration caused by gravity, is always pointed down. So in that case, if we're paying attention to direction here, g is going to be equal to negative 10 meters per second squared in this case, right? Because it's pointed down and the initial velocity, which is pointed up, okay? So let's go ahead and write some things down here. So it obviously told us that it has a speed when it leaves the ground. It has a speed of 48 meters per second. So that's going to be the initial velocity of the water. Now, the final velocity we have to imply, and that might not be immediately obvious to you. When an object is thrown up in the air, it always comes back down, right? Well, it's constantly slowing down as it goes up. And at the peak, when it reaches its peak, it pauses and it's motionless just ever so briefly. Okay, so the velocity at the peak is actually 0 meters per second. So we can actually say here that the final velocity is 0 meters per second. Another way to do this problem would be to say that the final velocity is negative 48 meters per second, because we could say that, okay, it goes up with 48 meters per second, it slows down till it hits 0. Then it's going to come back down and speed up at the exact same rate. So by the time it gets to the position where it left the ground, it should be traveling the exact same speed, just in the opposite direction. So you can kind of do this problem either way. Now I'm going to go ahead, and we talked about what g is and what that means. I'm going to put in negative 10 meters per second squared because it's traveling in the opposite direction. And then this is asking us to solve for how high can the geyser shoot, which is delta y. I forgot to underline these things here. So how high? And so now we have everything we need. Okay. Again, we're going to go through our process. Does this problem involve a change in position? Yes, we're solving for it. So we eliminate the first equation. Now we're choosing between equation 2 and 3, 1/2 at squared or 2a delta x. So does this problem involve time? It did not give it to us, and we're not solving for it, so we cannot use the 1/2 at squared equation. We're going to use the same equation we used in the last problem. So vf squared is equal to vi squared plus 2g delta y, okay? So here I can plug in 0 is equal to 48 meters per second squared plus 2 times negative 10 meters per second squared times delta y. And I apologize, my stylus is doing crazy things today. Okay, so we want to go ahead and square the 48. 48 squared is 2,304. And then again, because we have an addition sign right here, we want to subtract that off there. So we're going to subtract 2,304 from each side. Okay, so now we have negative 2,304 is equal to negative 20, so that's 2 times negative 10 times delta y, okay? So now we can divide by negative 20 on each side. Okay, and that's going to give us delta y, or the vertical change in position, is 115.2 meters. Okay, so let's say that you did not make g negative in this problem. So if you didn't catch that and you just plug in 10 meters per second squared, you would have gotten a negative displacement. So you would get, delta y is negative 115.2. That should kind of be a red flag to you. You should think, well, wait a minute, that doesn't exactly make sense. And then you might be able to catch that and put in the negative sign on the 10 meters per second squared. You would lose a point for having a negative sign there to say you had a negative displacement when it's going up and the initial velocity was positive. So you want to pay attention to that. Okay, let's go ahead and take a look at this next problem here. So baby blue jay sits in a tall tree awaiting the arrival of its dinner. As the mother lands on the nest, she drops a worm toward the chick's mouth. The worm misses and falls from the nest to the ground in 1.5 seconds. How high up is the nest? Okay, so it's obviously given us the time here. Time is 1.5 seconds. It's asking us to solve for the vertical position of the nest, and then it doesn't really give us anything else, right? So we have to imply some things. So first thing is, what is the initial velocity of the worm? It was dropped from rest, therefore it is 0 meters per second. We cannot imply anything about the final velocity. Okay, the final velocity, again, remember, is not 0 when it hits the ground. We're talking about the final velocity, the maximum velocity, just as it hits the ground or right before it hits the ground. Okay, and then the other thing that we know is that g, the acceleration due to gravity, that worm is going to accelerate at 10 meters per second squared naturally because of gravity. Now you might be thinking, well, why isn't the 10 meters per second squared negative in this problem? So in this problem, it didn't give us a positive initial velocity or a negative initial velocity. So we get to kind of decide which direction is positive or negative, right? It's all relative. It doesn't, as long as you define that direction. So in this problem, I'm defining down as the positive direction, right? So I'm saying that down is positive. Now, if you want to do all of your problems where up is positive and down is negative, by all means, you can do that. So you could make this negative 10 meters per second, in which case your change in position would be negative. So in that case, you would basically be defining the tree branch where the nest is as position 0, and then below it is negative and above it is positive. And that might make more sense to you. It doesn't really matter here. I can say that down is positive and up is negative, and therefore this is the nest. Anything above it is negative, anything below it is positive. So it doesn't really matter. But in the last problem, it specifically told us that up was positive by giving us a positive velocity. So we had to use that, if that makes sense. So on this one, let's go through our process here. Does this problem involve a change in position? The answer is yes, because we have to solve for it. So we're going to eliminate the first equation, the base acceleration equation. Second question, does this problem involve time? Yes, it gave it to us. Therefore, we're going to use the 1/2 AT squared problem or equation. So delta y, vertical change in position, is equal to initial velocity times time plus 1/2 times gt squared. Okay, I'm subbing in delta y for delta x because this is vertical. I'm subbing in g for a. All right, so we're solving for delta y. The initial velocity is 0, so this whole thing right here is going to be 0 plus, and I talked about that in the equation video, but when that initial velocity is 0, this just becomes 1/2 times 10 meters per second squared times the time squared, which is 1.5 seconds squared. Okay. So really all we have to do here is, and when your initial velocity is 0 on this problem, the equation essentially becomes delta y is equal to 5t squared. right? It makes it very simple. And why is it 5t squared? Well, 1/2 times 10 is 5, right? So, and then it's multiplied by the time squared. So that becomes a very simple problem there. So we'll do 5 times the time squared. So 1.5 squared times 5 is going to give us 11.25. So that means that the nest is 11.25 meters above the ground. Okay. All right. We'll go ahead and do our last problem here. One more. It says a giraffe who stands 6 meters tall. So that's going to be our delta y there. So delta y is 6 meters. Bites a branch off a tree to chew on the leaves, and he lets the branch fall to the ground. How long does it take? How long does it take for the branch to hit the ground? So we're going to be solving for the time here. Okay, and that's going to be in seconds. Normally I like to put the units there. So again, we got to imply some things. What's the initial velocity of the tree branch? It was dropped from rest, so it's 0 meters per second. And then we also know that that tree branch will accelerate at 10 meters per second squared because of gravity. Again, we are not given an initial or final velocity that indicates which direction is which, so I can go ahead and make that number positive and not have to deal with negative numbers. So let's go through and figure out which equation we need to use. Does this problem involve a change in position? Yes, it gave us 6 meters of vertical change in position. So we eliminate the first equation. Second question, does this involve time? The answer is yes. We have to solve for it. So we're going to use the 1/2 at squared equation again. So delta y is equal to the initial velocity times the time plus 1/2 times gt squared. Okay, so this time we're given 6 meters as the vertical change in position. So 6 meters is equal to, again, this right here is going to be 0 because the initial velocity is 0 plus, I'll go ahead and write it out again, but we could just make this 5. 1/2 times 10 meters per second squared is 5. Okay, and then we are solving for the time. And don't forget that it's squared. We'll have to use the square root later. So again, we could simplify this and say, okay, well, 6 meters is equal to 5t squared over here. Okay, and then we will need to divide by 5 on each side. So I'm going to go ahead and flip this and just put t squared over here. So t squared is equal to 6 divided by 5, okay, which is 1.2. And then what we need to do is we need to square root each side so that we can get rid of this squared right here. And then you'll find that the time it took for the tree branch to fall was 1.095 seconds. So I went out to 3 decimals there because I'm trying to be a little more accurate. But if you put 1.1 seconds, that's totally fine. Okay, so there are your 5 math problem examples for acceleration. You now have practice problems to do, and you don't have to do them all right now. We'll do those in stages. Make sure to let me know if you have any questions.